Okay, in a previous lesson we looked at the matrix transposition problem and we gave a cache-aware algorithm that performs this matrix transposition using only n divided by b IOs. In this lesson we're going to develop a different algorithm which is cache oblivious and achieves the same IO performance. Okay, let's quickly remind ourselves of the strategy that we used in the cache-aware algorithm. Okay, so what we did was we partitioned the matrix into these tiles, submatrices of size t by t, and then we're going to read all these pairs of tiles that fit together into the internal memory, swap all the elements and write them back. Okay, so for instance this one, well, it has to be swapped with itself, or the next one which has to be swapped with the opposite tile. Okay, and after doing this for all the relevant pairs of tiles, we're done. And the crucial element of the algorithm was to pick this tile size really large, this t, such that, well, 2 tiles should still fit into the internal memory, but actually 2 tiles should essentially fill up the whole internal memory, so that we can after that do lots of swapping before we have to do more IOs. Okay, so the cache oblivious algorithm actually wants to do the same thing, but the problem is the cache oblivious algorithm does not know the size of the internal memory. So the idea is the following, and again this is something that also works for other problems where you have something that is cache aware and based on tiles, then often to get a cache oblivious solution you can use a recursive algorithm. And why would a recursive algorithm be good? Well, the main idea is that the recursion is going to make the problems smaller and smaller. Right? So at some point automatically the problems, well, you start with the whole problem, it gets smaller and smaller and smaller. So at some point it will be small enough so that it exactly fits into the internal memory. After that, the algorithm is going to continue to be recursive, right? Because it doesn't know that now everything fits in the internal memory, but sort of automatically when you've read everything, even though you make recursive calls, this is all happening in the internal memory, so no IOs are being done. So this is the plan, and let's see how this works for our matrix transposition problem. So here we have the matrix that we want to transpose, and in a recursive step we would say, okay, let's partition it into 4 smaller submatrices, as you see here. And for now, let's focus on these 2 submatrices in the top left and bottom right corner that we have to swap. Okay, we want to swap the elements in these 2 submatrices, and what we're going to do is we're going to look at how we can do this recursively. Okay, so how do you do that? Well, also these submatrices are going to be split into 4 smaller, even smaller submatrices each. And now to swap these 2 things, we just have to swap the 4 pairs of smaller submatrices that we get. Okay, so let's look at how to swap this particular pair. Well, again, we can do it recursively. We divide both into 4 smaller submatrices and swap each of these pairs. Okay, so this is the general plan. To swap a pair of submatrices, we have to swap 4 pairs of, well, submatrices of half that size. So this continues all the way, I mean, from the algorithmic point of view, you get 4 recursive calls, and this continues all the way until you have, well, let's say submatrices of size 1 by 1. Right? Or actually, in this particular case, depending a little bit on the exact size of the matrix, it could also be 2 by 1 or 1 by 2. But that's not that important. Just think of it as you continue until you have submatrices of size 1 by 1. Okay, so this is the plan. Well, there's one slight exception that we already saw before, namely that submatrices on the diagonal are treated a little bit differently, right? Because for the other submatrices, similarly for the tiles, they have to be swapped with another one, but the ones on the diagonal are swapped within themselves. Okay, so how does it work if you want to do it recursively? Well, again, you partition into 4 smaller pieces of size half the original size. But now you only have 3 recursive calls, right? 1 call that is sort of no longer on the diagonal, and 2 calls where you still swap within themselves. Okay, so here we have only 3 recursive calls. So here you see the algorithm, and well, let me not walk you through it. It's pretty easy. You can read it in the course notes. What is important to see is you have these 3 recursive calls. And if you look at the parameters, you will see that they are on submatrices of half the size of the original call. So if you had a T by T matrix, then you have 4 calls on matrices of size T over 2 by T over 2. And, well, depending on whether what you're looking at now in this call is on the diagonal or not, you're going to have a 4th recursive call or just have 3 recursive calls. Okay, so this was our algorithm. And what I claim is that, well, this algorithm, similarly to the cache-aware algorithm, performs only n divided by b IOs. Okay, so let's try to prove that. And what we're going to do is, since our algorithm is recursive, we're going to prove this using a recurrent relation on the number of IOs. Okay, so I define T of T to be, if you have a call on a submatrix of size T by T, the number of IOs that you do. Okay, and I want to have a recurrence formula for this T of T, and that you see here. And what is very important to realize is that the base case, well, the base case of the algorithm is when you have, let's say, a 1 by 1 submatrix, so when T equals 1. The base case for the I/O analysis is when everything fits into the main memory. Okay, so this recurrence for a cache-oblivious recursive algorithm would always have as the base case if the subproblem fits in the internal memory. Okay, so let's see when this is the case. Well, actually, we already saw that before. We had this formula. So let me briefly explain again where this formula comes from. Well, this 2 is because in a subproblem, actually, we're reading in 2 submatrices. So we need to fit 2 of them in the internal memory. And then the size of one of these submatrices, if it has size T by T, well, it's T, number of rows, times per row you have T plus maybe these blocks sticking out. Okay, and this together should fit into the internal memory. Okay, so this is the base case, the condition for the base case. How many IOs do we do in this case? Well, the first thing what you could do is to say that, well, if you look at it more carefully, then the number of IOs is 4 times T over B plus 2. But you can also think about it in a different way, and that's kind of instructive, that the base case, this condition on T, was chosen in such a way that everything exactly fits into the internal memory. Right? So you know that the T is such that we're going to read essentially M, capital M, size of the internal memory items, because everything fits, and so that's the number of IOs. Right? So instead of this expression in form of T, we could also simply say, well, we know that the T is such that we get M, side of the internal memory, divided by B, number of IOs. So let's write that. Okay, so then the only thing we need to add is, to this recurrence, what happens before it fits into the internal memory. Well, that's pretty simple. We simply have 4 recursive calls. Okay, so this is the recurrence that we're going to get. And, well, I'm not going to show you how to solve it. I assume that hopefully you know how to solve such recurrences. But the solution that you will get is T of T is n divided by B. Initial call it's T squared divided by B. Initial call T is M, so T squared is N. So indeed we get the N divided by B that I promised you. Okay, so this is pretty nice. we saw a, well, in this case, recursive algorithm, a cache oblivious algorithm that performs n divided by b IOs. And as I explained, this recursive structure is something that you could also use in many other problems to achieve good IO behavior. So this is a cache oblivious one. What we're going to do in the next lesson is, well, the assumption for cache oblivious algorithms is that you have some optimal replacement policy, right? And here we said, well, one replacement policy is that you read everything into the internal memory, then do all the swaps when it fits, and then write it back. So we have some assumption that it works like that. In the next lesson, we're going to look a little bit more in how these replacement policies work, and that this assumption is actually not so unrealistic as it may seem.